Posso provare? Si sente? Da in fondo si sente? O si sente meglio? Uguale? E allora parliamo di questo. Non posso. Sì. Okay, shall we start? Good morning, everyone, and welcome to the 10th Young Researcher meeting. Can you hear? Fine, over there. Okay, cool. So we are very happy to be back in Vergata to celebrate this 10th anniversary because, yes, it has been 10 years of the meeting, and it's particularly a pleasure to be in Tor Vergata because it all started in Tor Vergata. This was an idea, the Young Researcher meeting, of a group of PhD students in Tor Vergata, and so we are happy to be back. So what's the Young Researcher meeting? Many of you already know because I can see in the crowd faces of people who already attended this meeting before. But anyway, for the newbies, this is a meeting, an informal meeting, yearly meeting, itinerant meeting, organized by young researchers and students for young researchers and students. And the idea is to have an informal platform where you can actually discuss progress in several active research fields related to physics. So as you have already seen, the program is a dynamic program and quite a polyhedric one with contributed talks, with many posters, in fact. This year we have 60 posters, about 60 posters. Then there are roundtables, workshop on specific topics, and invited talk by speakers reporting cutting-edge research topics, and also visits to world-class research facilities in Italy. So, but why we decided to create a young researcher meeting? First of all, to encourage a bottom-up approach. So this meeting is entirely organized by young researchers and students, and all aspects of it, mainly, are handled and managed by them. Starting from the fundraising, meaning looking for funding, and then, identifying a location, a venue for the meeting, decide and define a scientific and social program, eventually advertise the meeting, and finally, even all the work that concerns the publishing of the proceedings that every year get published on the Journal of Physics conference series is handled by students and young researchers. So a bottom-up approach. Another aim of the meeting is to foster the discussion and the interaction between students and young researchers. Often in academia, these two classes of people live segregated and separated, so we really want them to interact because we believe there is an added value to this. And then very much differently from other conferences that tend to be extremely specialized and co-limited on a specific topic, we try to keep the topic of the meeting pretty broad trying to bring complementary expertise together. And in fact, this is why we asked you to prepare and to pitch your talks in a way that they can be understood by colleagues of yours, which, however, do not work exactly on your same topic, because there are techniques, there are methods that can be shared, and you never know what you get. And this kind of exercise, trying to explain your research to people working in topics that are not exactly yours, really helps you developing science communication skills that are always useful. Eventually, the very grand idea behind this meeting was actually to create an international network of students, of young researchers that may interact and may keep in contact and share information on jobs, on work opportunities, on research fields and research trends. And this is why also in 2016, we founded this non-profit association known as International Physicists Network. And this was meant actually to support the organization of the Young Researcher Meeting and to allow people who have attended the Young Researcher Meeting to keep in touch and keep organizing events and promote collaboration together. So what has been the Young Researcher Meeting across the years? As I told you at the beginning, it all started in Vergata. So it was the 2009, you might recognize some of us. I am here, Francesco is here, and we were really just a bunch of us, mainly people coming from Rome and a few colleagues, friends from the UK. We had no sponsors, so no cool coffee breaks and stuff like this, but we really enjoyed this kind of meeting. The fact that it was a very informal way of communicating and sharing information, that we decided to repeat this the year after at Sapienza University. There we got sponsored, and therefore we got coffee breaks, and the number of participants increased. This is why we decided also to keep it on, and we had the third edition, again back at Vergata, where we got support from the INFN and the physics department. So the number of people at that time, and some of you probably can recognize themselves in this picture, the number of participants grew enough that the year after, when we moved to SISSA in Trieste, we decided to enlarge the meeting that started as a one-day meeting, and it became a two-day meeting. I don't know if you noticed, the number of dots, of red dots on this chart increased slowly, meaning that every year we were able to reach some new institute and get the participation of people coming from different places. So there was also a fifth edition, once again in SISSA, and you may notice the number of dots increased. And this was again the case in which the number of participants was high enough to call for an extra day of meeting. And indeed, for the 7th Young Researcher Meeting, we went to L'Aquila, hosted by the GSSI, and we had a three-day meeting. Notice that really when we moved to GSSI, we started to have people participating from outside Europe. Can I do this? Yes. After the GSSI, there was touring, a lot of sponsors, we had a great participation, and when it's like that, you already know that the year after, you're going to have another day of meeting, an extra day of meeting. And this was the case again for the 8th meeting in Cagliari. So at this point, the meeting becomes a 4-day meeting. Notice the cool picture at the Sardinia Radio Telescope. And this was last year in Salerno. So probably you noticed that across all these images, the number of dots have increased, and we have participation from people all over Italy and not just Italy. So really in the idea to create this, we have been moving really in the idea to create this network. So we've got some interesting press coverage across the years. But anyway, this is what has been in the past. What about the meeting we are going to have in these days? Well, it's difficult to guess, but there are a few more dots here and there in this chart. And this year you can see that the meeting is supported by, again, the University of Vergata. We are back for the 10th anniversary, and by the IMFN, but also the Solar Physics Group and the Progetto Lauree Scientifiche. And we also have the support of ACCA. There is a company. You'll see people from ACCA later today. So what we are looking forward to. So today we are here at Villa Mondragone, this historical villa. We will have a guided tour of the villa before lunch, when we will take also the group picture. So please stick around so we can actually fill up this chart with a cool picture. We have two very interesting sessions of contributed talks, one on astrophysics and cosmology, the other one on matter physics. And in the afternoon, we're going to have a round table on the link between physics and industry. We will have representatives from HR, from companies, but also there will be physicists, even ex-organizer of this meeting, who moved from academia to to industry. So they will bring their testimony and they will tell us about their experiences. After the round table, people from ACCA will also be here if you are interested in showing your CV and discussing with them possibilities to get a job outside academia. People from HR will be here and can discuss with you if you have any question or if you want to present even a CV to them. After the round table, eventually we go for the poster session. This year, as I told you, about 60 posters, so a very rich poster in one session. And watch out, on Friday there will be the Best Poster Awards ceremony. And this is just for today. The other days will feature, keynote speakers like Massimiliano Lattanzi of the INFN of Ferrara, and Claudia Taccalite from Marseille. We will go and visit the laboratories in Frascati, the INFN laboratories in Frascati. We will enjoy a social dinner right in front of a Roman aqueduct. On the other hand, we are in the Eternal City, so what else you would have expected? Eventually, for the one of you who stay till the end, on Friday afternoon, there'll be a guided tour of ancient Rome. So I hope I didn't forget anything, but anyway, we will be here and we really hope you'll have a great meeting. Before starting, however, let me just present you the crew. These are the people you will see around these days and to whom you can ask any question and any curiosity and help. I know it seems weird since we haven't started the 10th meeting yet, already talking about the 11th meeting, but what usually happened during the last edition was that people attending the edition got enthusiastic about it and wanted to actively participate in organizing the next edition. So we are really looking for a location and an organizing committee for the 11th Young Researcher meeting. So if any of you feels up to the challenge, let's say, and anyway, to the amusement, because it's extremely interesting and I wouldn't say funny, but it's an interesting experience anyway. So please come and talk to us and volunteer yourself. We of course provide every year any kind of support we can. Okay, just a notice for tomorrow. I don't know if you can really see the map, but tomorrow, unfortunately, for as much as we like the historical villa, tomorrow we will not be here. We will be at the scientific macro area in Tor Vergata. What we recommend is for you to take the subway, Metro A, till the last stop, Anagnina, and then take the bus 20 and get off at Sorbona, right? From there, you'll see a little gate. You cross the gate, you go through a parking lot, and there, from there you'll see signs. We will put signs all around so you don't get lost, okay? Anyway, we will upload this map on our website, so you can actually check it out also on the website. So on behalf of all the organizing committee, we wish you all a great meeting. So I think it's time to start, okay? And I'm very happy to leave the microphone to Professor Anna Di Ciaccio, who is the director of the IMFN section, the IMFN division of Rome Tour Vergata, which has supported this meeting and this event for several years. And please.
Okay, good morning to everybody. A really warm welcome to all of you. I am happy that this conference, in the meantime, got so successful, also thanks to you, and I really hope that we'll get more and more international. I mean, I work in Atlas, in an international project in energy physics, and when I go to Geneva, to CERN, I see a lot of young faces. Actually, the strength of the group are people like you. And so I really think that young people like you should have more opportunity to discuss, let's say, propose also new idea, how they see collaboration among us, and one idea that I was discussing with Marina, I don't want to interfere with your work, is to organize more table discussion, just to see, I mean, which is your role. Your role is very important. I mean, you think I am a young student, I am a young researcher, I play not a big role, I mean, but because I don't have let's say, a high-level position, I cannot decide anything. But you are the one that you are doing the physics. I remember that the best time that I had in my life, when I was young like you, and I was working that time in an experiment with the Nobel Prize, and I was sent, I mean, to different universities in the world, I mean, and this was the more emotional events of my life. So, coming back to this meeting, I am happy that you are here in our university. Our university is a young university, only 40 years old, order of magnitude. And sitting in our university, there is this Institute of Research that is Istituto Nazionale di Fisica Nucleare that finance research in several branches of physics. Particle physics, astroparticle physics, theoretical physics, nuclear physics, and multidisciplinary physics. And we have a strong collaboration with the researcher in the Department of Physics. So, I mean, we are really, I mean, happy that we have this privileged position and we can collaborate with the researcher in our department. Our university is young, but still has already got 40,000 students and basically from all possible faculty. So, I am pretty sure as a sponsor these events because recognize the value of an international collaboration. So I hope you can enjoy in this meeting. I mean, you are today in this place that is, you know, an historical place that belongs to our university, where we have major events like Laurea Honoris Causa, and we assign some prize, and there's a villa from, as you will hear later on, from Renaissance, where the Pope were coming in summer because it was too hot in Rome, and here instead this fresher and cooler. So, and also this villa was declared Gregorian calendar by the Pope Gregory VIII, I guess. So has even lived such an important event. So good luck with this event and also for the next years. I hope, as I said before, it's becoming more and more international. There will be a larger participation, and you, I mean, we have some fruitful discussion for next edition, and even I suggest that you can go abroad Italy. I mean, being such a large collaboration, you can think about to organize somewhere else. Okay, so enjoy the meeting.
So, good morning everyone. We can start with the first session, that is Astrophysics 1. And first speaker, I called Stefano Carletta to come here.
Ok, sono 20 in totale? 15. Okay. All right, so good morning, everyone. Let's start from here. Thank you to the organizers for this nice event. And let's try to start. So as you can hear here, well, maybe not here, but to see, my name is Stefano Carretta. I'm a PhD student in space science. And actually, I am involved in space mission design and mainly space trajectory design. This is my task is to design a particular class of this trajectory that I will show you in a little while. But the key point of this presentation is that these trajectories, they have been used and designed for spacecraft. So actually, objects that we design, we know how they work, and we know how to place them. We try to place them in the right positions in space to do our stuff. The idea is, can we use the same tools for designing some asteroid capture missions? Why asteroid captures? We'll see in a while more details, but because there is some interest from the scientific world to have some hands-on experience on asteroids. I mean, to collect some data, collect materials, but actually to work with asteroids is pretty complicated as far as they are far from the Earth. So actually, can we use these techniques to get closer, or better, to move closer the asteroids to Earth and to place them in the orbits we want so that we can operate our missions the best way? This is what I want to talk to you, and I would like to have some inputs from you if you have any, because my point of view is that of the designer of the mission, but maybe some elements that are necessary for people working on this kind of scientific aspects of the mission, I don't really know. So this would be the great input I would love from the audience. So this is more the summary. Not this, but we will start from a description of asteroids, and we will see how we can design the capture in a chaotic environment. Then we will see how to tailor this capture, point 3, in the model of the circular restricted three-body problem. And finally, we will have an extension to the elliptic four-body problem, because this is the typical Sun, Earth, Moon scenario. All right, well, why are asteroids interesting? I can give you two main reasons. First of all, they can be hazardous objects. So we want to know if one of the asteroids that are really small mass objects in space, planetoids, if it is moving too close to Earth, and eventually it can impact. Now, of course, if it can impact the Earth, it means that it has been captured by the Earth. And the concept of capture, I think, is pretty, let's say, normal. It's pretty straightforward. It is a body, a celestial body, is attracted by the gravitational force of another one, of bigger mass, of course. And because of the huge difference of mass between the asteroids and Earth, and all of the other planets in the solar system, the attracting force of the asteroid towards the Earth is highly negligible if compared to that of the Earth. So this is one example of Florence asteroid. There is also some scientific interest in them because of the minerals that they are typically composed of rocks and minerals, and so there is interest in discovering more and more about the composition, to learn more, to have a deeper insight on our solar system. And as you can see, this is a typical scenario of a close encounter of Florence asteroid with the Earth. So what we see in this yellow circle is the orbit of the Earth, the orbit of Florence asteroid getting closer to that of the Earth. There's no impact, of course. You hear about it, so there was no impact. But actually, this is a typical scenario. Now we have huge families of asteroids, so we have many. We will now focus on near-Earth asteroids because they are, of course, the most interesting one for this purpose. The closer to the Earth, the less the energy we need to move them closer. And in particular, there is, you see, a lot of families. Amor family is the one Florence asteroid belongs to. So as you can see, it doesn't cross. Okay, in blue, you have Earth orbit. Amor asteroids, they do not cross Earth orbits, but they move close. But because of their small mass, actually their trajectory is not stable, or better, it is somehow highly perturbed by that of the other celestial bodies. So actually it can happen that because of some combination of relative position of these bodies, perturbations, they change that little bit the orbit of the asteroid so that it gets towards the Earth in this case, or any other planet. And this is in fact a kind of like a very likable event. Now let's focus on one family of these asteroids, that is Aten family. And in particular, this family crosses the orbit of the Earth. So what is the first step in capturing an asteroid? The first step is actually to reduce the radius of the orbit of the asteroid, or better, to reduce the semi-major axis, in order to move that closer to the Earth. But actually, this would be the simpler option, but it requires kind of a high energy. There is another option, that is move it closer to one equilibrium point of the Sun-Earth system that we will discuss, and it's the L1 liberation or Lagrange point. To do this, we have to reduce the size of the orbit, the semi-major axis of the orbit. So there is a variety of ways we can do this. It is somehow an expensive operation because of the size of the orbits. The simplest one, but we can discuss other ones, of course, is to apply some delta V, which reduces the semi-major axis. So it decelerates the orbit, we reduce the velocity, we reduce the kinetic energy, the orbit squeezes. And we move from the larger orbit to a smaller one, which doesn't touch the Earth, let's say. It's closer with respect to the Earth from the perihelion in this case. And it's actually moving to L1. And we will focus, for capture, we will focus the behavior of the asteroid once it enters this region that is called the equilibrium region. Why are we interested in moving the asteroid in the equilibrium region instead of redirecting that straight to the Earth? Because we have some strong control on the trajectory of the asteroid if it enters this region, and we will see. And we can model all of this phenomenon using the circular restricted three-body parabola model. Okay, so once the energy of the asteroid is small enough, because of its negligible mass with respect to that of the Sun and the Earth, now in this case it's better to consider the Earth plus Moon system. Because of the distance, they will be more or less 1 point mass in this first approximation. We will see a more refined model later. So actually, these trajectories, as you can see, they are pretty much chaotic. So it means that they will spend some time around the Sun, some time around the Earth, or Earth-Moon in this case. But it's actually possible to define some conditions in which the capture, the trajectory, it is confined about one of these two celestial bodies that are called the primaries. And this is called a capture. Now, the capture can either be ballistic if it occurs spontaneously. And of course, you can understand that the probability for having a ballistic capture is pretty limited. But once we understand how ballistic capture works, we can apply criteria for powered capture. And so we can take advantage of the natural dynamics in multi-body environment to reduce the cost of the maneuver and to change the orbital parameters of these chaotic orbits. And we will see some applications. So in order to model the problem, I don't want to go too much in detail in this because it's mathematically a little heavy. We can model the problem of the three bodies using the Hamiltonian approach. And now the Hamiltonian approach is pretty, let's say the Hamiltonian variables, they are positions in the three-dimensional space and the conjugate momenta, P, which is basically a mixing of velocities in the physical space and position. it would be nice to work with physical dimensions, but it's not always convenient, even if they give some good description that is easy to understand. Actually, we have to apply some transformations. This is in particular the region we will apply this transformation. So L1 is an equilibrium point of this system. We have in total 5 equilibrium points, but we will focus on L1 because it's basically the point that produces the result with the smallest energy. So if we now zoom onto that region, you can see that you have this green boundary. This is just an extract of the previous one. Because of energy constraints, the trajectory can only be inside this green boundary. Now, if we linearize, since this boundary is the region surrounding an equilibrium point, we can linearize the system about there. And actually, we can use the linear system, and we can apply this Siegel-Moser coordinate transformation to rearrange the equations of motion into this shape. So the Hamiltonian function, whose derivatives provide the dynamical behavior, it consists of 3 elements, which are 3 integrals of motions. So these are constants. Now, playing with these constants, so with the values of x1, y1, 2, and 3, we can define different orbital behaviors. And in particular, we can see that, okay, alpha 1 is the value of x1. So if x1 is equal to 0 or approaches 0, you can see that in color we have a time scale. Actually, the body is captured because you see that the time that it spends about one of the target body, it reaches unit 1, which means 15 years in this figure. So actually, with just playing with one parameter, we can determine if the body is captured or not. And this is how a capture orbit looks like. So it moves from the equilibrium region, this is L1, and it starts rotating with some chaotic behavior, but confined within one of the primaries. For instance, the Earth-Moon system. The same concept can be then applied onto the Earth-Moon system to capture the body onto about the Earth or about the Moon. So we will be able to move our asteroid from close to the Earth to close to the Moon. But we have much more control. Actually, by playing on the energy of the 3 different integrals of motion, so the quantity of energy that is dedicated to each one of them, we can have strong changes into the inclination. So we can move from flat orbits to basically polar orbits, or close to polar. The maximum inclination we get, it depends on the energy. Okay, now we said the value of x1, that we call alpha 1 when it's some fixed value, it will depend on some variables, including, okay, the positions, like y0 and x0, and the velocity, v and u. These are the in-plane velocity, along x, u, and along y, v. So actually, we can change these velocities in order to change the value of alpha 1. So if this was the initial behavior, applying some thrust, even for original different values of x1, we can obtain the same result. So we apply alpha 1 to set alpha, we apply delta v's, changes of velocity, to set alpha 1 equal to 0. And as you can see, starting from any point within the equilibrium region, we can get captured. So it means that if our asteroid is injected in the equilibrium region, whatever happens by applying a delta v, and this is a small delta v, centimeters, tens of centimeters per second, it can be captured. Once it is captured, we can change its inclination, as we saw before. Or we can also apply, by these formulas that are a little complicated to develop, we can also apply some other acceleration to change the other orbital parameters. Now, suppose that this was the original orbit, the capture orbit, once you inject the asteroid into the equilibrium region. This is a flat orbit, inclination is roughly 0. This is evaluated for different positions of the Sun, which has a perturbative effect on the orbit. Applying these accelerations, which in the end produce a change of the velocity, of course, by some thrusters, We can move from this orbit, this is flat and with a very large periselenium, to this orbit, which is a high inclination orbit, chaotic, but with some orbital elements that are fixed, and fixed as we want. So in this case, we move to a periselenium that is 100 meters of altitude, more or less, 100 kilometers of altitude, more or less, and an inclination roughly close to 75 degrees. And as you can see, if you have some confidence with these numbers, the delta V provided, they are very small. The order of magnitude is meter seconds, so hundreds of meter seconds. So if compared to a classical maneuver to obtain the same maximum inclination and maximum reduction of the pericenter, it would get almost 2/3 more to get the same results. So it's a 60% saving. Now, someone might argue, okay, we have seen this technique for capturing asteroids, but you split the problem into two phases, from the Sun to the Earth-Moon system, and then within the Earth-Moon system. But this is actually an approximation. Of course it is. But the good point is that the behavior, so the topological behavior of the phenomenon, it can be extended to the four-body problem and including eccentricity of the orbits. This is because of a theorem. So actually by an infinite number of basically 3 canonical transformations, we can reproduce the same results considering the Sun, Earth, Moon system all together. So it will be a 4-body environment with eccentricity, and we will get exactly the same result. So it means that once we have solved the problem in the Hamiltonian system, setting alpha 1, h1, h2, whatever the value we want, we just apply the transformation back to the physical space, and in the end, we obtain what are the initial position, the velocity to provide to get the result either in the 3-body system or in a 4-body system, and conceptually also in a 5, 6-body system. Actually, the 4-body system is the most interesting one to us because it is a typical example of the Sun, Earth, and Moon system. So here I close my presentation, and please, if you have some questions, just ask, and I hope you enjoyed that. Thank you.
Okay, there are any questions for Stefano? If not, I have one. If you can move back to slide 5.
Take some time to do it.
No, no more. Okay. You told us that you are studying the asteroids in the equilibrium region. Just a curiosity, why is it easier to study this region if their behavior is studied in other region, and with what approaches?
Okay, an equilibrium region exists around any of the libration points. So actually, we could study them in here, but also on L2, or equivalently on L3. The point is that within the equilibrium region, the natural dynamics of the asteroid, or any negligible mass, it is a combination of the pull by the Sun and the Earth, for instance, so by the two bodies. So actually, since it is extremely not stable, it is in an unstable environment, then small changes, but accurate ones, they can take advantage of the instability to produce the desired effect. And this is why there is some strong savings in delta V. The second thing is that if you want to apply the same changes by classical Keplerian orbits, so by Bowman transfers and stuff like that, first of all, the delta V is higher. Secondly, you are neglecting the perturbative effects of the other bodies, but still you will have to apply correction. In this case, we take advantage of the perturbation. So actually, it is included for producing a proactive effect.
Thank you.
Thank you.
Yeah. Question?
Thank you very much for your presentation. Very interesting presentation. Can you go to the slide 17? No, 13, sorry, 13, I guess. Yes, 12, sorry. Okay, you said, if I understood, that once the asteroid is captured, it moves on a chaotic orbit.
Yes.
Right. So, how can I plan a mission from Earth if the orbit is chaotic? Chaotic means that we cannot know exactly where the asteroid is once the orbit is reached.
Correct.
Yeah.
Okay, this is the point. The first step is to move the asteroid within the equilibrium region. There we can play the game. Once we are in the equilibrium region, we can capture that. And at that point, most of the game is done. The orbit is chaotic in a sense that we don't know the position, or better, we can predict by numerical analysis the position of the asteroids in time, but it will not be as stable as a Keplerian orbit. Now, the point is that by applying some delta V's, like the one in the slide 13 that you saw, we can fix some orbital parameters. We cannot fix all of them because we have the Tisserand parameter that relates the semi-major axis eccentricity and inclination, but we can fix two of them. So actually, yes, there is a chaotic motion, but nevertheless, once we fix the orbital parameters to get typically the desired radius at pericenter and inclination, then the last delta V to be applied is that for circularizing the orbit. And here is where the, let's say, increment in the savings of delta V is applied, because we move the asteroid to the best position where we can circularize the orbit, to the best conditions where we can circularize the orbit. And then we apply everything. So yeah, the orbit is chaotic, but within some constraints.
Thank you very much.
One more question.
Thank you really for this presentation. So you mean that you need to reach a hot bifurcation in your system to have a circular orbit?
Okay. The energy required for the circular orbit would correspond to a bifurcation in the equilibrium region. But actually, this model works if the energy level is below that of bifurcation. So it means that the periodic orbit about the liberation point is not an halo orbit, but it's just a Lissajous in the 3D space. So very small energies. Actually, the system is robust with respect to high energy. So if we wanted to save delta V, reducing less the energy of the orbit, we could obtain the same result with some more difficulties. There is a paper by Vadim Kaloshin regarding this. But actually, the point is that you can circularize the orbit and get the energy you would have at bifurcation when you're far from the point of bifurcation. And this is the trick. So we take advantage of the natural dynamics in the equilibrium region with small energy. Small energy means also small delta V expense. Once we get to close to the Earth, for instance, or to the Moon, depending on where we want to go, with two of the desired orbital parameters, there we circularize. But we do not suffer any bifurcation problem because we are very far from the equilibrium region at that point. So at that point, we are captured by one of the parameters. But yes, in principle, the energy would spread the curves to the bifurcation.
Okay. And thanks again, Stefano, for the presentation. For your next speaker, Andrew Miller.
Okay, thank you. My name is Andrew. I'm a PhD student at University of Florida and Sapienza, and I'm here to talk to you about gravitational waves and how we're using machine learning to detect gravitational waves from young neutron stars. So we need to talk about a lot of background so you understand what gravitational waves are, how we use them, why you should care. So we'll talk about that first. So gravitational waves are essentially energy that comes from the bulk motion of matter. And this matter is accelerated in some way that is asymmetric. So the classic example is a binary system. So you have two objects that are orbiting each other. So we have two black holes, two neutron stars, and they are slowly moving towards each other, and eventually they will collide. And so as they are moving towards each other, they are losing energy due to gravitational wave emission. And this energy comes from the fact that the orbit is not symmetric with respect to some axis. and that's in the center of the two objects. And so what you have is gravitational waves that are emitted, and then this leads to the orbit slowly coalescing, that the two objects are getting closer to each other and speeding up. They are a solution to Einstein's field equations when you linearize them. So in an analogous way to electromagnetism, you have wave-like solutions to the field equations, and these waves propagate at the speed of light. But unlike electromagnetism, these waves are very weak. And we know this because the gravitational force is the weakest of the four fundamental forces. And so you don't actually, it doesn't interact very well with matter. And so you have so when we measure gravitational waves, we're measuring extremely small displacements in space and time. So we're talking 10 to the minus 21. So 1 part in 10 to the 21. We need to measure this kind of displacement. And so this is for example, this number is the peak strain that we measured when we measured the first binary black hole merger 4 years ago. So now we should talk about why we should study gravitational waves. Gravitational waves provide us a probe of a different portion of the parameter space that we did not have before. Electromagnetic observations, as well as observations that we have on Earth, they can probe the so-called weak field region. So when stuff is not moving very fast and is not very massive. But gravitational waves, they come from things that move, at least the detectable waves, come from things that move very fast, relativistic things, like black holes and neutron stars. And there are also questions that we can only answer with gravitational waves. So for example, that in order to test relativity in these different weak field and strong field regimes, gravitational waves are the way that we can do this, because they come from the bulk motion of very relativistic objects. So it helps us answer questions like, are there other theories of gravity that might be right, that predict different things about, for example, how quickly the gravitational waves travel, if there's some deviation, or there's some interaction that we don't fully understand. We can use gravitational waves to determine this kind of interaction. The second thing we can talk about with gravitational waves is we can talk about what kind of remnants that mergers produce. So this is in reference to binary neutron star mergers. So we don't have a good handle on, we have an understanding of what the remnants could be of neutron star mergers, but we don't understand in all cases what they actually will be. And so we can use gravitational waves to identify with no ambiguity, if we can make detection, as to what the remnant actually is of a binary neutron star merger. And this is important. Electromagnetic observations cannot do this because you typically have the sources are very far away, where the electromagnetic radiation is weak when it gets to Earth. And so with gravitational waves, you have a smoking gun identification of what the remnant is. Then we should ask the question, so okay, gravitational waves are really cool, but can we actually detect them on Earth? And the answer is yes. And so we use an interferometry. And so this actually is in Pisa, or near Pisa. It's an interferometer. It's very pretty. It's 3 kilometers, so it's a big L, and each arm of the L is 3 kilometers long. So it's very massive. And these tubes are all vacuum. So it's extremely expensive to build, as you can imagine. And we'll show that how it actually works. And so what we know from relativity is that when a gravitational wave passes through anything, so passes through the Earth, for example, it will distort the shape. And this is an exaggeration, but essentially the wave, when it passes through, so the wave is propagating perpendicular to the page, it stretches and compresses things in different directions, depending on what the polarization of the wave is. And so the principle behind gravitational wave measurements is you want to measure this kind of displacement. And the way that you do this is using interferometry. So you have a big L, essentially, and you have a beam, which is here. It goes through this beam splitter, so it splits the beam in 2. And then the beams propagate in different directions, perpendicular directions. They hit some mirror at the end of this arm. They come back and they rejoin, and you measure here the interference pattern between the 2 light beams. And so if the gravitational wave passes, you will see this motion, which means that in one direction, matter is compressed, in the other direction, it's stretched. And so what you see at the detector is a difference in arrival time of the the laser beam. And so this results in a phase shift, and this is something that you can actually measure if you have precise enough instruments. So this 10 to the minus 20 meters you need to measure. And so this is very, very precise, and these instruments are very good because they can do this. But now I want to talk about specifically gravitational waves not from binaries, but from neutron stars, which is not as hot now as binaries, because binaries are ones we detect, we know the waveform, we know what they're supposed to look like in the data. But from neutron stars, They're very interesting because they're extremely relativistic, and we don't understand a lot about them. So we don't understand how the pressure and density change as a function of radius of the star. We don't know what they're made of. And so gravitational waves allow us to answer these kinds of questions. And so typically the model that we have for gravitational waves that come from a neutron star is that there is some mountain, so some deviation from spherical symmetry, and then the neutron star is spinning very fast. So as the neutron star spins around at some rate, about 1,000 revolutions per second, this mountain is emitting gravitational waves because it is deviation from spherical symmetry. There's a time-varying moment of inertia of the system, and this is what causes the gravitational waves. So a spherical object will not emit gravitational waves no matter how quickly it's moving, but because you have this deviation from spherical symmetry, you have gravitational waves. And so this deformation can be caused by, well, it's not so well understood, but any kind of break in the crust. So if the magnetic field is very strong, it can actually, it can cause craters in the crust. And this can, as the neutron stars rolled around, it will emit gravitational waves. So now I want to talk about, so we talked about, okay, what they are, gravitational waves are, how we detect them, but how do we actually analyze the data to find gravitational waves? And so this is where we use machine learning. And why machine learning? And the reason is because we don't have good models of what the neutron star behavior actually is. So we have some modeled searches that basically assume Taylor expansions of the frequency behavior. So the spin down of neutron stars, the rate at which the rotation rate is changing is quite small in theory. And so you can use this model and you can search for signals that follow this kind of behavior. But if you don't trust your model, if you don't think your model is perfectly right, which is no reason to think that it is perfectly right, then you need some kind of unmodeled way of searching for gravitational waves. And machine learning provides you this. Once you train a machine learning method to detect some signal or some image that you want, it can generalize to find new things that aren't exactly the same as what you had before. And okay, this is the motivation for why we use machine learning. And also it's very trendy now, so everyone's doing it. So we should want to do it too. And it's had a lot of success in gravitational wave physics. So it's been able to identify glitches in the noise, because our noise is very high, non-stationary. And we can also detect binary black holes with it. This was shown in some paper a while ago. But some key questions that are not answered by a lot of the conventional machine learning papers is how much did you train? Is there a point where it no longer makes sense to train a machine learning algorithm? So the point is that with the machine learning, you give it a lot of examples where it learns the behavior of the image or the signal that you want it to find, and then it generalizes to find new things. But it's not clear how much you need to actually, how many examples you need to give it. Moreover, it's not clear what kind of architecture, what kind of construction of your network or your algorithm that you should use. And it's also not clear how how different constructions and how different the networks will give you different results, and how robust is the network towards different things that you don't understand. So we know, okay, that machine learning works very well, but we don't know in our specific circumstance how robust it is and how well it can actually detect signals that deviate from the training set. And then finally, probably the most important thing is that our noise in LIGO Virgo is very non-stationary, which means that we cannot predict the noise at any future time. We have some idea of what it's like. There's some Gaussian component of the noise, but the point is that the noise is always changing. And so unlike conventional machine learning problems where you can just give blurry images or you can give a wide range of images, we have a finite amount of data and we have noise that's always changing. And so we need to quantify at what point we need to actually, how much we need to train so that we can guarantee some false alarm probability that's reasonable. So the method that we choose to use are convolution neural networks, where the principle is essentially that you have an image. The input to the network is this image, where you can see frequency on the y-axis, time on the x-axis, and the color corresponds to strength of the signal. And so you can't really see, but there is a signal here. It starts here and it goes like that. So the input to our network is this time frequency map. And at each layer of our neural network, you have a convolution, you have a selection of local maxima in each square of this image. But it's a black box because you don't understand what it's actually doing in the network. You understand the input, you understand which layers you put, and then you understand the output. And the output for us is a probability, or something that can be interpreted as a probability, which basically tells you what is the likelihood that this particular example has a signal, a gravitational wave signal, or not. And the signals that we're using are very rapidly time varying because we're looking for signals from young neutron stars. So they decrease 150 hertz in frequency in the course of 2,000 seconds. So this is a very, very high spin down. And so now I want to talk about some results that we have from the machine learning. So the biggest question we wanted to answer was how much do we actually want to train? And so what you see here is efficiency on the y-axis, so how many signals you get right over the total number of signals that you test on, as a function of your training set, the number of training injections that you use. And the color of what you see is the strength of the signal. So each of these lines basically corresponds to a particular amplitude. So how much deviation and distance will the signal give you in the detector? And so what you see is that as you increase the number of training injections, you don't see much of a difference in your efficiency, which means that the problem that we're trying to solve with machine learning is actually quite an easy one. It's just trying to identify a curve in the previous time frequency map that I showed you. And so the point is we don't need many signal maps. And the implication of this is that we don't have to spend a lot of computational resources to simulate signals and to train on many, many sets of injections. Because a lot of the conventional Google neural networks and these things, they need a lot of examples to actually have good results. But we can achieve good results without having to train on many examples. But this comes at a price, of course. And so we want to understand as well how good the neural networks are in comparison to something. So we have some method that can also detect gravitational waves. We want to compare the network's performance to this method. And so what you see here is a sensitivity curve, what you saw in the last class. You have efficiency so this is a sensitivity curve. You have efficiency as a function of the strength of the signal. So signals down here we cannot see at all. Signals up here we can see very well. And you have different curves here that mean different things. But the point is that you want to look at the curves here. The red and the purple one are the neural network that we trained and the conventional method. And so what you see is that they are extremely similar. Sometimes even the neural network performs better than the conventional method. But the caveat is that the false alarm probability is much higher. So with the neural networks, you have a very good chance of identifying something that's not something that's just noise as having a signal in it. And this is a huge problem with neural networks and when comparing them to conventional methods. So the point is that we need to be very careful with how we use neural networks when we do this kind of data analysis because we have a very, very high false alarm probability. And just to make another comparison, if you look at the green curve, this is actually quite good. It's outperforming everything. It's also a neural network, but it's the case where you have fixed background noise. So the noise in LIGO and Virgo, the noise is always changing. But if you train and test on only one kind of realization of the noise, you will find that you have very, very good efficiencies. And this is basically provides an upper limit for how sensitive the network could be in the most ideal case, where you don't have any kind of changing background noise. Unfortunately, we do. This is why you have curves that curves that perform much worse. The network performs much worse when you actually train and test on different realizations of the noise. And then the last question I want to answer is, can they be wrong? And I alluded to this before, but yes, they can be wrong, and they can be wrong very badly. So how we control the output of the network, the output is a probability that the network, that the image has a signal or not. But we can control this as kind of like a detection statistic. So this detection statistic is plotted on the x-axis, and the false alarm probability, so the number of times that the machine learning thinks that there's a signal there when there's not, is plotted on the y-axis. And so what you see, and then these curves correspond to different frequency bands. And so what you see is this threshold is dependent on the frequency band that you use. Why? Because each frequency band has its own noise problems. So there are more lines in certain bands because of the resonant modes of the mirrors. There are a lot of specific things about the detector that are encoded in different frequency bands. So also, for example, certain types of noise are more dominant at higher frequencies than lower ones. And so a network that we have to understand to use this for a real search, what kind of threshold we need to place on our detection statistic to still achieve like relatively good false alarm probabilities and still good efficiency. And so I will end there by just saying that the network is good enough in the sense that it's comparable with existing methods, but at higher false alarm probabilities. So we can use the networks as a first level in our search to generate triggers that can be followed up by some method that has a much lower false alarm probability. And I will end there. So thank you very much.
Thank you, Andrew. Are there any questions for Andrew's presentation? One.
Actually, okay. In slide 14, you showed several curves of efficiency with respect to energy. Now, the red and purple violet curve, actually, the efficiency of the red curve is higher for a given energy value.
Yeah.
In any case, except roughly about 0.6.
Yeah.
Is there, it's just a curiosity, but is there any deterministic reason why this happens, or is it just happening in this case?
There is some determinism. So these curves are plotted for a given detection statistic threshold. So we put the threshold at 0.9, so we have to be like 90% confident that the map contains a signal for it to be classified as detected. And so this can shift, depending on which threshold you use, this can shift your curve in one direction or the other. So the red curve essentially is fixed because this is not dependent on any kind of detection. Well, it is a different detection statistic, but it's basically fixed. But the machine learning, there is some deterministic nature because you are controlling a lot of the output and the input. So you're also training on different amounts in different trials. So the error bars on these curves are probably about on the order of a few percent, which would be then consistent with the error bars on the purple curve. So because it's limited by how much you're testing on and how much you train on. So there is some determinism that goes into it.
Any other questions? If not, we can thank you, Andrew, again for your presentation. We can call Sarah Saracino, speaker.
Sì, il microfono che ok.
So, hi everybody, I'm Sara, and I want to thank the organizers for giving me the opportunity to present some of the results that I achieved during the last years in collaboration with Bologna and the University of Bologna and the University of Liverpool when I'm working right now. So, I want to start my talk just to making a comparison between ground-based telescopes and space-based telescopes. So in terms of pros and cons. So when we focus on space-based telescopes, we know that we can actually have a really short view of the universe. Just because we are in the space, but we need to take into account that we can have just a very small collecting area, and it's of course really expensive. But if we move on a ground-based telescope, we see that so the situation in terms of cost is much more achievable because it's less expensive, and of course it's much easier to maintain and upgrade all the instrumentation. But we need to remember that there is a very big cons that is due to the seeing of our observation, because we cannot reach a very high spatial resolution just because we are on the Earth. And so the question now is, we can solve these two counts in both sides to try to have an improvement in such observations. And so for the space-based observations, Of course, no, we cannot improve because we cannot so remove these really expensive costs. But from the ground-based observation, so we can actually do a very good job by using adaptive optics techniques in order to, so just to remove the seeing of our observation, to try to reach a very high spatial resolution even from the ground, really comparable with the one from space-based telescopes or even higher. So just to show you how the adaptive optic technique works in a really basic way. If you look using a ground-based telescope, you look at one portion of the sky. Actually, you see that the Earth's atmosphere, so it's turbulent. We have turbulent layer, and so the wavefront that is almost flat of the light coming from these distant sources is in some way distorted, and so you cannot, so the spatial resolution is completely lost, as you can see here. So this is the real how this portion of the sky looks like, and once it passes through the Earth's atmosphere, this is how it looks like. So you cannot distinguish and resolve all the stars that are in this field. But if you apply these very basic techniques, so just using a deformable mirror and a wavefront sensor that in the real time are able to to distort in an opposite way the wavefront of the light in order to become flat again. So you can actually restore the spatial resolution. And so this is great because it's just from the ground. So this is a very simple case. So when it starts a few decades from now, but now we are in the present, but we are looking into the future, and so we want to move from simple adaptive optic techniques and so systems to multi-conjugate adaptive optics. So it means that we don't need only one reference stars to make this kind of correction, but we use a combined, multiple guide stars that are natural if they are available, or artificial, so laser guide stars, in order to reach the diffraction limit of your telescope. So has slightly depends on the diameter of your telescope. So much larger is your diameter, and so you have a higher spatial resolution. And so for today, we have this only instrument that is at the Gemini South Telescope in Chile, that is equipped with this Gemini GEMS camera, so is equipped with multi-conjugate adaptive optics, and it has an aperture diameter of 8 meters. But when we look into the future, we know that ELT, that is this telescope that we will build, and we have this first light in 2025. It has an aperture diameter of 32 meters, and so if we are able actually to reach the diffraction limit of this telescope, so to use all its diameter, we can really do a good job in the future. And so we need to think about it's the right time to think about and to start to analyze these kind of images, because it's the future. So this is just a comparison so just to start to be familiar on this. So a comparison of two observation of the same field. This is a curiosity is the very center of a crowded globular cluster that is a sample of 10 to the 6 solar masses of stars. And so this is the really center, and both the observations are from the ground, but without and with adaptive optics. And as you can see here, the improvement in terms of angular resolution is remarkable, just because you can solve each individual stars even in the very center of these private regions. So I want to present you my project, that is to start analyzing a sample of bulge globular cluster. I'll show you later what the galactic bulge is and so on, but trying to combine space-based capabilities, so from the Hubble Space Telescope and these MCA observations from Gemini, which is the only one instrument I keep right now. And so there are different goals for this project, but today I want just to focus on the last one, that is the most interesting one, I think, because it's to try to test astrometry, which seems, which means to be sure that all your observations, you are able to recover the exact position of your stars, objects, distant objects, or what you want in your images. And so your telescope needs to have a very good astrometry in this sense. And so to measure, to measure proper motion with this instrument. So just to make a very brief introduction on what the galactic bulge and globular clusters are. So globular clusters are these kind of objects, so 10 to the 6 solar masses in stars are very crowded, especially in the center, and I want to look on that in the galactic bulge, that is one of the most inaccessible regions of our galaxy, is the most central one. And of course, you cannot see nothing in the optical because it's obscured at least at 10 magnitude in the optical band. And so the idea is to try to combine the near-infrared capabilities of these MCAO instrumentation with the capabilities of HST, just because we need high angular resolution to go really into the core of these central regions. So the problem is, once you want to look on these MCA observations, you need to think about how these observations really look like in this sense. So for many years, all the astrophysicists tried to use HST just because it was easier, because you don't have any variation, you don't need to take into account the closed loop of the adaptive optic that sometimes can be wrong. And so there are different problems like this, and it's just much easier, and 25 years is enough to take into account everything. But so we are looking into a new instrument with a new technique. So we need to take into account, for example, a very big problem, that is the geometric distortion of the camera. And so I realized when I started to look into these images that they were highly distorted. And so I tried to, and this is the distortion that is up to 40 pixels in the edge of this camera. This is 4 chips of the camera, and so I tried to remove them with an algorithm, and at the end we can really reach an accuracy of 1 millisecond. And I want to stress that this solution, that is just an equation with all the coefficients, you can actually use this equation for every kind of science you want to do with these instruments. And so now I go very very quick in these details, but I want to present you one case that is, so NGC 6569 is just the name of a globular cluster, this one in my sample, but for which I try to do this kind of job. So I want exactly to see in this kind of field of view how stars, which are the stars that are belongs to the cluster instead of the field stars. So just to try to separate cluster members from field stars interlopers. So in the last 25 years, so this kind of job has been done using different epochs with space-based instruments, so with HST. So I try to do this just using HST for one epoch and MCAO, so this camera for the second epoch, and they are separated of 5 years at least. And so I'll try to do this, and I want to highlight that this is the first attempt without any information, so we actually don't know what of those stars are field stars or are cluster members. And in this sense, here you can see that after applying the distortion correction that I showed with you before, you can actually separate the cluster members from field stars in the interlopers. That in this case, for this kind of field, you can see that is bulge and disk of our galaxy. But so now after this, you can really do a good job for different so in different topics. But I don't want to enter in detail on this because I want to show you something that is even more interesting. So we were lucky in this sense because we had one of these clusters in our sample that was for different issues, was observed twice with the same instrument. And this is the only one target that is in the Gemini archive, observed twice with the same instruments at the distance of 5 years. So just for an issue, we were really lucky. And so I tried to do the same thing in this cluster, but just removing HST completely and using both of the epochs using ground-based telescopes. So only these two observations, and as you can see here, you can actually do a really good job even without HST at all. And so this is all the field of view that we had. This is the field and the cluster. So we can actually, again, separate quite well cluster members from field stars, and we can actually know without HST how to do this kind of stuff. And this is the first time that we can actually do it, and we have to think about it because it's the future. So I want to leave you just with these take-home messages and to remember that many more results are still to come, so just jump on it. And thank you, everybody, for their attention.
Thank you, Sarah, for the presentation. Are there any questions? If not, I have one curiosity. When you spoke about the distortion geometric of the camera and the algorithm that you used to correct it, yes. It's just a software correction, or is a mixture of software and hardware with the adaptive optics?
No, it's a software correction. And so actually it's something that you cannot apply a priori, because it sometimes changes for the seeing condition of the observing light, for the position of the target in the sky. So it's something that you need to do after, yes, a posteriori. And in this sense, so we just got this kind of equations to remove the distortion in just using one data set that we had, but we try to use the same the same set of equation in different cases to try to see if they really work quite well or not. And it seems that they are quite stable, so we can really do a good job even if we are looking in a different direction with different conditions, spatial condition, and so on. And so is the reason why I say that you can, in principle, use these equations even if you are looking to a quasar or, I don't know, an AGN or something that is really different, just because of the configuration of your camera and so of the optics of your camera.
Okay.
Yeah.
Thank you very much. If there are no other questions, we can thank Sarah again. Okay. Now we will have an half an hour break, so we can recombine at 20 to 12. So the people that has not already placed your poster, you can profit of this half an hour to do it. See you in half an hour. Thank you.
Lasciamo andare metti la slide.
Allora sì, quindi non so se hai visto il prompt. Allora, le mie linee sono gli ammassi standard, diciamo. Quelle rosse sono secondo me utilizzati, che abbiamo identificato con l'articolo, e quelli blu sono degli set di ammassi strani, che hanno dei set strani, che sono però ammassi di calcio, e quindi pensiamo che questa stranezza sia dovuta al fatto che la separazione da un ammasso dovrebbe essere problematica. Quindi comunque sono per e poi c'è una e poi c'è anche un'altra sedia per 3 ammassi del metallo intermediate, che ho scelto in base a una roba di tavolo, quindi in base a una metodologia, e in cui ho inserito anche il faro qui e il mio qui, la Camex, e io posso lasciare il secondo analizzato. Che non ho analizzato prima quindi già dei modi che l'hanno uso però dividendo purtroppo sì, forse no, c'è qualcosa nella forma. Assolutamente. Sì. Sì, era un trucchetto.